My name is Nicole Dölker. I work at the Institute of Catalysis and Petrochemistry at the Spanish National Research Council. We are the coordinators of the BIORING project. I am part of the coordination team, and as a project manager, I am generally in charge of the day-to-day activities and coordination and follow-up with all the partners. So I'll give a very brief introduction to BIORING, what it's all about, and then I now see someone else's screen. Do you see my screen?
Now, yes.
Now, yes. There was some kind of
there was some interference. Okay. Yeah. So I'll just give a brief introduction on BIORING. For those, I know that some people already joined the first meeting or know us from other events, but for those who don't, so you know what this is about. Then later you will hear in more detail about the sustainability and LCA aspects of the project. Okay. So what is BIORING? BIORING is a project that is focused on engineering high-performance bio-based coatings from renewable building blocks. It is a CBE JU project started in June 23. So we now just reached our midterm mark. BIORING is a research and innovation action, so we started at a rather low TRL and working our way up to actual coatings. Bio-based coatings, we are producing bio-based coatings derived from different building blocks of a variety of biomass-derived feedstocks. Where the feedstock is not the main focus of our project, the feedstock itself, but more the versatility of the approach. And our products are supposed to be or will be UV curable coatings. For, in our case, as a use case, we chose construction and automotive sectors. So our consortium is formed by a combination of large industries, SMEs, research centers, university, and IRI as an industrial association. I think it's a rather specific and characteristic aspect of BIORING that although this is a research and innovation action, we have a strong presence of industrial partners. Because although we are working on a very novel product that started at lab scale, we aim to really apply it in a pre-industrial context in a real life use case. So why BIORING? What is the context? Why are we doing this? So bio-based coatings actually, at the moment, they only constitute a very small niche market. So the coatings market is really large, but bio-based products only constitute about 5% of the total coatings market. And there seems to be a bit of a problem of the bio-based products taking really off and gaining importance compared to other bioplastics and other bio-based products. There are some attempts of high-performance polyurethane coatings, but as soon as they exceed a biomass content of usually 30–40%, there's generally a problem with the functional property. So it's not easy to create a high-performance coating with a high bio-based content without compromising its functionality. So this is our aim here, because there has been clearly an observation that there is an increasing demand, which is also reflected in a number of EU calls that have been opened lately, focusing on subjects around bio-based coatings. So our objectives are, BioRing is based on, let's say it's based on a number of different columns. On the one hand, what we are developing is a platform of renewable building blocks rather than one specific coating. So the BioRing idea is that we have specific building blocks that we are developing, but it's built in such a modular way so that in the future, if new bio-based monomers come into the market, they can be incorporated into our systematic approach. But on the other hand, we are not stopping there. We will also produce, the idea is at least 2 formulations with a very high bio-based content. So the final aim is about 95% bio-based. And then our other 2 very important columns is, on the one hand, sustainability assessment and LCA, specifically early LCA. And this is also what this workshop is going to be about, because when working at very new products, projects starting at a low TRL, we have this problem that we need to guide the project also with renewability and LCA and life cycle analysis in mind, but without having all the data, because we cannot do it retrospectively with the data already present. We have to start already when we are starting the work. So this is an important issue in this project, and this is also what we discuss in our workshops. This goes hand in hand with process modeling, which enables us to get an outlook for future scale-up without actually being at a point where we can scale up. So while we are still working at lab scale, the process modeling allows us to detect bottlenecks, to detect, to work on strategies for scale-up. And finally, last but definitely not least, our aim is to actually apply our coating formulations onto use cases in the automotive and in the construction and furniture sector. And we all, of course, also want to identify other market opportunities for the future. So this is, in a nutshell, our approach. We have our platform, which is a combination of components that are bio-based and already commercially available, and others that are developed in BioRing, which are then combined to first biopolymers, and those biopolymers are used in coating formulations, which can then be applied in the automotive and in the construction and furniture sector. And at the same time, we are studying effects as recyclability and biodegradability. So this is where the project is. As I said, we are now right in the middle. So the last year and a half, we have focused strongly on the synthesis of monomers. So we are now at a point where we have synthesized all the required monomers, and we are able to provide samples for polymerization and coating formulations. And that part of the project will now follow up with optimization, scale up, and especially purification methods to make it more efficient. We have also started with the first polymerization samples, so we have some samples, but this is now going to be a very strong focus on this during the second half of the project, where we are going to work on further increasing the bio-based content and optimizing the formulation to find this equilibrium between high functionality and higher bio-based content. As I said, the conceptual design, the techno-economic assessment, and the safety and sustainability studies are a strong pillar that has been accompanying BIORING from day one and are going to continue until the last day. We have done a lot of initial work, prospective LCR, identifying critical substances in the safe and sustainable by design approach. And we will now start incorporating also data that comes from the project itself, going beyond the purely prospective part.
Thanks, Nicole.
Just to conclude, so just to understand where this innovation workshop falls in this structure. So this is a number of a number of activities we have planned to reach out to other stakeholders and generally people who work in the field. This is the second innovation workshop, and then we have the option to plan additional workshops by demand. So these two were planned from the beginning, and then we will go ahead a little bit according to what our needs and demands are. Furthermore, we're going to have recommendations to publish some recommendations to EU strategies on circularity and safe and sustainable by design approaches. And we will also publish on our website public summaries of all our deliverables so that people can follow us a bit more closely what we are doing. And in the end, we will have 2 fully public deliverables on safety, sustainability, and LCA evaluation. So this is where we stand, and we are now here at the second Open Innovation Workshop. And with that, I will close my presentation and give back to Andrea.
Thanks, Nicole. So I would move to the next presentation from Marc Borrega, SuperBark Coordinator and VTT. While we are recording the event, at least all the talks, I hope no one has anything against it, otherwise let us know, of course. So Marc, the floor is yours.
Yes, one second, I'll put it in presentation mode.
Perfect.
Yeah. So how much time do I have?
3 to 5 minutes would be perfect, if you can.
Okay, then I'll be brief. So good morning, everyone. My name is Marc Borrega. I'm a principal scientist and project manager at VTT, and I'm acting as coordinator of the SuperBark project. SuperBark stands for safe, sustainable, and high-performance adhesives and coatings from bark. So we use bark side streams as raw material to develop our adhesive and coating formulations. So SuperBark is a project also funded by CBE. VTT is the coordinator, but in the consortium, we have a total of 12 partners coming from 8 different countries. So we are quite well spread out over Europe. We have research and technology organizations. We have some large industries. We have SME, and we have 1 university as well. Our total budget is $4.5 million, and this is a 4-year project, started in September 2023 and will run until August 2027. So since time is short, I'll get to this picture here to explain what we are doing and what we are trying to accomplish. So this is basically project scheme showing the whole value chain. So as I said, we start with bark from softwoods, like pine and spruce trees. This is our raw material. Then we use these bark residues, which are residues from the forest industries, in really large amounts, in the, something like around 15 million tons of this softwood bark available in Europe. So we use that as raw material to do an extraction process. It's a patented technology from VTT. We do an alkaline extraction, and our goal is to remove the polyphenols, mainly tannins, but also other phenolic compounds. So these polyphenols are actually extracted from the bark and then recovered using a membrane technology. And these polyphenols are then used to develop different types of formulations for adhesives, which are then used in wood panels, like plywood, particle board, and MDF. MDF is medium density fiberboard for a wide variety of industries like furniture, construction, transportation, and so on. The main goal here is to develop these adhesives, which have at least 95% bio-based content, and to replace current fossil-based and harmful chemicals, which are used to make adhesives. For wood panels, typically formaldehyde-based adhesives. If we look at the lower part of the scheme, so when we do this extraction of the polyphenols from the bark, we have also a residue, a bark residue, which is mostly composed of cellulose. So we use that residue to make nanocellulose. And this nanocellulose is then used as an ingredient for the formulation of coatings, with the main application in wood products, but also in packaging paper to provide barrier properties. So again, we are targeting at developing at least 95% bio-based coatings and replacing fossil-based compounds or chemicals, and specifically some replacing harmful chemicals like fluorinated compounds, for example, that are used for barrier packaging. So all this development work is guided by a safe and sustainable by design assessment. We do also different types of modeling to ensure the replicability of the different technological developments, and also to facilitate the integration of the solutions into the market. One of the aspects of this safe and sustainable by design is the LCA that you will now hear very shortly. So yeah, this is in a nutshell what we are doing. Of course, now the time was very short, so you can follow us we have our own website. We also have social media accounts, so you can follow our progress there. And if you have any specific questions later on, you can either contact me and I'll direct you to the right people, or you can also contact Laura from CLIC. She's somewhere here. I cannot see her now, but she's our communication, dissemination, and exploitation officer. So that was it. Thank you.
Thanks, Marc. Thanks a lot for your overview of the SuperBark project. I think we can go now into the theme, the topic of the workshop, with 3 presentations dedicated to LCA and how this is applied in BIORING and SuperBark. So I can give the floor to Cyrille Jovita, that will start with the BIORING, and then Federico Busio that will discuss about SuperBark approaches. So Cyrille, maybe you'd like to start? We can see your screen now, and you just need to put it in presentation mode. No, Cyrille?
Yeah, I'm kind of sharing the screen just right now, so give me a moment. Can you see my screen?
Yes, but put it in presentation mode. Still, okay, great.
Is it
okay?
Is it
That's
okay
good.
now?
That's okay.
Okay, well, welcome and thank you for your participation today. So my name is Cyrille Durand from TEMAS Solutions. In the BIORING project, we are kind of focusing on the accessibility assessment of the value chain. So I will make a really short introduction to the purpose of what we're doing, and then my colleague, partner in this consortium will be Jovita Moreno will be introducing this a little bit more details what this LCA is doing in terms of more details. So, but first of all, this is I want to start here more from the market side. in this project, we had the opportunity, not we, but another partner from this consortium made a study about looking at the benchmarking. So what is out there in the market in terms of bio-based coating, and of course they were interested in multiple aspects of this coating. The first, the functionality, the performance, but as well we had an interest in understanding how companies were communicating about the sustainability of this bio-based resin, and it was quite interesting. So I just wanted to have a snapshot, because at the end there's an outcome of this study, regarding the sustainability and how companies were communicating. We kind of found that these sustainable claims on this commercial bio-based resin coating are quite limited to the bio-based content, and yet the definition of the bio-based content is referring to multiple reference. I give you a couple of examples where some companies were claiming some percentage of green carbon or biocarbon content, so they were referring to the ISTM about the measurement of carbon 14, but some others were mentioning the percentage of bio-based content, but that was calculated from mass balance and referring another certification. Some others as well were communicating the percentage of bio-based content, but it was as well another type of certification. So it was, to put it straight, a little bit messy, and it was relatively impossible to compare with a science-based approach, how these different bio-based resin were performing in terms of sustainability. So that was a kind of a good learning. So there's clearly a need for more LCA information that need to be provided to the customers with, of course, more meaningful, but as well life cycle based as well, and science-based information to really be able to compare, the sustainability of this bio-based product. So that was a good learning from the market. So, we know that there are some challenges. It's not that the companies don't want to provide this information. It could be as well related to the fact that there are some challenges to obtain this LCA data, and that gives kind of a purpose of the work that we do, and the purpose of this kind of a discussion we're having today is not only how we can develop LCA methodology and of course manage this database limitation to provide assessment and guidance early in the material development. So when companies are really developing bio-based resin, they have this LCA as a support for the assessment and for the guidance during the innovation project. But as well, of course, at the end of the innovation project, they have enough LCA data that are available, so they can claim some sustainability aspect of this resin. Now, having kind of made a quick introduction and some key message, I just wanted to tell you here in this slide what we are doing. So this slide is a bit heavy, but if you see in the middle, we are really using as a base the safe and sustainable by design framework from the GRC that was developed by the European Commission. So we are kind of pioneering this framework, because it's been released a couple of years ago, so still in the testing, but that's very interesting framework, as it provides, here you can see different steps in terms of, looking at different aspects from human health, environmental health, and LCA assessment. So this step from 1 to 5 that you can read there in the center. But as well, it requires to have a tier approach, because as you going forward in the innovation process, you gain and you develop more data points. So you need to do the assessment with some iteration. So of course, the topic of today is the low tier because we're doing an early LCA. So that's what we've been doing, with the early TRL of this project. From TRL 3 to 4 potentially. That we'd call the stages of BIORING. So we did a few things there. First, of course, understanding the life cycle of the benchmark. So you really have to understand the benchmark, what it is about and how it is. And it is good here because you have quite some available information from the industry. But then when it comes, of course, to understanding how sustainable are the BIORING materials or chemicals that are candidate for the BIORING solution, then it's here we face some challenges. So we use some fortnight some early we say some early tools that you can use when you have mostly qualitative approach. Not of course enough quantitative data. So we use early for ANMA and the LICARA innovation scan that are kind of a ready-to-use tools that give you some hotspots to look at. But more importantly, and this is what Jovita will develop in the next few slides, we did use some information that were modeled by some technical and digital tools like the Aspen by our partner PDC, and this information was used for starting some CA, and this is actually what Jovita will be talking now. So Jovita, you can continue.
Okay, thank you. Cyrille, maybe you can maintain your screen and to go to the next slide, and it's faster.
Sorry, can you see your slide?
Yeah, it's perfect. Okay. Good morning, everyone. My name is Jovita Moreno. I am from Associate Professor of Chemical Engineering in Universidad Rey Juan Carlos in Madrid. And together with Cyrille, another partner, we are developing the LCA activities in the BIORING project. Our activities here are divided mainly in two main parts, on two main tasks. We are now developing the first one. The first one is to perform our preliminary LCA about the BIORING formulations. To understand our work here, I think that it is important to take in mind the general picture of the BIORING scheme. And this is this figure that you can see in the slide. We have several bio-based compounds, very critical for the final formulation. So we need to mixer and reacting these compounds, and then also to perform some physical operation, and then to obtain the final BIORINs or bio-coating formulation. So during this process, we need to consume several chemicals and also to use the energy. So to perform a cradle to grave or a cradle to gate LCA approach, so we need to recover a lot of information, as you know. So the first problem for us here, and I suppose that for all the analysis that we are going to discuss today, is that to have information about the environmental profile of the bio-based chemical that we need to use to formulate the bio-coating, okay? So which are the impact associated with these bio compounds, because usually they are not available in the usual database like EcoInvent and others. So we need also to work on that. And now this is our main task in the BIORING project. So we are working together with our experimental partner to know about how we can obtain this biochemical in the laboratory scale, which chemical we need to use, which purification step, and all those information that is critical to synthesize this bio-based compound, which are also critical to obtain the final BIORING formulation. So this is our main task now today in the project. So once we have the information about this compound, we try to scale up this data using, as Cyrille explained before, using some process simulation tool like Aspen and other simulation software. And this is very important because we can move on from the lab to a higher scale. So this is quite important to have more realistic information about the equipment and about the energy consumption. And then we use those results to build the inventory to perform the LCA of this biocompound that we need to formulate the coating. So Cyrille, please go to the next slide.
You have 2-3 minutes more here, Jovita.
Sorry?
You have 2-3 minutes more.
Yeah, yes,
I'm
finished. Yeah, once we have the the information of the different key chemical, we use the same approach, lab scale, process simulation, and LCA approach to obtain the environmental profile of the biocoating formulation, to the final biocoating formulations. This is our approach to perform this preliminary LCA, and the most important is to obtain some interesting, some valuable feedback for the experimental partner, to improve the laboratory pathway and to improve to optimize this experimental procedure that they are performing in the lab. Okay, and this is the first part that we need to do in the BIORING project. And finally, please, Cyrille, go to the next one. In the last year, this is the future task. Once we have optimized the BIORING formulation, we select one of these pathways to perform the final sustainability evaluation. In that case, we need to analyze not only environmental indicators, but also social and economic, to have the general picture of the real sustainability of our biocoating. And of course, in this last step, we will have to compare the environmental profile of this BIORING formulation with those corresponding to the fossil benchmark, to have the the final comparison and to demonstrate the sustainability of our solutions. And this is all from my side. Thank you.
Thanks a lot, Jovita. And I think we can now move to Federico Busio from LIGNIn and SuperBark, that will show us the approach of SuperBark to LCA. So Federico, it's your turn.
Yes, good morning, everyone. Can you see my screen?
Yes.
Yes. So I'm Federico Busio. I'm LCA analyst at the Luxembourg Institute of Science and Technology, and I'm computing the LCA part of the SuperBark project that Marc just presented, according to the Safe and Sustainable by Design framework. So as Marc explained during his introduction, the objective of SuperBark is to develop safe and sustainable bio-based adhesives and coatings that should be used for the production of particle board, plywood, and medium density fiber board, and also coatings again for plywood, either for transportation and construction, and also for packaging paper. Overall, the objective is to dispense with the use, for example, of PFAS in some of these products. So this it's quite as it presented, a complex project with multiple partners. LIST is responsible of the Safe and Sustainable by Design analysis assessment. It's split between myself for the LCA part and my colleague from the Health and Safety group, who is today not present. Pretty much our work will be to provide advice all around the three main work packages of extraction or production of bark-based components, work package 2, work package 3 with the production of the adhesives, and work package 4 with the production of the coatings, as well as with the production of the final product. So as I just explained, this is the work will consist in evaluating the impact from the extraction of polyphenols and the production of the final SuperBark adhesives, and again the extraction of the other component from the barks, which is bark-based CNF, and the production of coatings. And then again another LCA that would evaluate the production of the final product, both in the plywood, particle board, MDF, and both for the production of for the application, the use of coatings. So in total, there are 4 adhesives that are produced for different engineered wood products, 1 coating for paper products, and 2 coatings for engineered wood products, plywood for transportation and outdoor structure. Again, in this project, we are applying the Safe and Sustainable by Design framework. Of course, the Safe and Sustainability Assessment is the part that comes all along the project, starting with the safety assessment, which is done by my colleague for the step 1, 2, and 3, and then at the same time, there is an evaluation once the safety steps are passed. For some products, for the chemicals that pass the safety assessment, then we go into the step 4, which is the environmental sustainability assessment, which is what I do, whereas the techno-economic assessment is performed by the partner in VTT. So far, the project, as Marc said, is quite young, so we're only 1 year into the project. My personal experience into this project related to challenges in performing the LCA are first of all the inventory step, the building of the inventory for the different chemicals that are used by the chemists, by the people involved into the development of the SuperBark molecules. For me, sometimes to recreate the different materials and energy used to produce the precursors, or to produce these chemical substances that the chemists use, it's complicated, either because in the database we don't have the right molecule. Therefore, I would have to go and recreate the stoichiometric reaction from literature sources, and then of course try to compute that in the LCA. Sometimes you can directly obtain the product from existing literature material, but you never know whether the reaction that they used in this literature material is actually up to date and representative of the chemistry that the partner is performing right now in SuperBark. Therefore, when you don't have, sometimes you also approximate to the closest molecule. You use proxy molecules from EcoInvent, for example, database. But of course, a proxy is not the same, and this choice introduces biases in the final results. Additionally, I would say that the transfer of information, as was pointed out before, the transfer of information from lab testing to me, to LCA evaluation, is complicated. It's slow, and it's not responsive enough to the point of efficiently supporting the design phase sometimes of the molecule. So I'm slower in providing feedback. The limitation are also at the impact assessment method, in my opinion, because when we develop new chemicals, if the characterization factors do not exist in the impact assessment method, their impact on the environment and also on the health from, for example, ecotoxicity or human toxicity point of view, these are not characterized, and therefore we cannot capture the differences, the potential differences that exist between a fossil-based chemical or a bio-based chemical, all along the life cycle of the product during manufacturing, use, and finally disposal. There is also limitation to model the production process of the product, not just at the chemical product, but also at the production process. Data from a production company is complicated, is often incomplete, is often not shared, is protected, and when it is incomplete or approximated, of course, there are biases that are introduced towards the bio-based alternative. That's why there is a strong need for transparent production data of the reference product. Thank you.
Thank you, Federico. And interesting to see that there are common challenges across different projects. So now we can move to our other case studies from other projects. As a note, of course, these projects are all in different stages, at the end, in the middle, at the beginning. So you need to take into account this aspect when listening to the presentation. So the next presentation is from Léo Staccioli from ARDITEC and the LIGNICOAT project. So Léo, the floor is yours.
Okay.
Yeah,
can you see my screen?
Yes. Just put in presentation mode. Perfect. You can go.
Okay, all good. Okay, good morning, everyone. My name is Léo Staccioli. I'm working for the ARDITEC Association based in Nice, in the south of France. And today I will briefly talk about some of the challenges that we faced during the project LIGNICOAT, which is a European-funded project that we just closed in November. So this is how we'll proceed during the presentation. First, a quick introduction of myself. Second, I will talk briefly about the project LIGNICOAT, then the challenges related to the LCA applied to the project. And finally, I will show you some of the results. Sorry. Okay, so my name is Léo Staccioli. I'm a sustainability engineer for the ARDITEC Association. I primarily studied health and safety engineering, but I quickly focused on the sustainability aspects of different product processes and through different professional experiences, notably in France and Spain. So I have now 8-year plus experience in LCA, and I'm currently leading the environmental assessment in several European projects, dealing with bio-based material like LIGNICOATs, but also waste valorization, industrial techniques, wind turbine blade production. So basically, a wide range of different topics. So now a few words about LIGNICOATs. Basically, in these projects, we're starting from the lignin feedstock to produce several types of biocoatings for different purposes, such as fire protection, anti-corrosion, antimicrobial, or antiviral applications. In between, we have several sub-steps, more or less complex, I would say, to produce different intermediates like the polyols or the polyacids. Then we also have the resin production, the bio-additives that we mix with the resins, and finally the biocoatings. So as you can see from an LCA perspective, this is quite challenging with a lot of processes, to assess and a lot of data to collect, with the differences also in the scale production. So this was interesting to assess. Okay, since we don't have much time, I didn't want to make a list of challenges that we faced during the project, so I decided to focus on the difficulty to work with the different data sets and the need to sometimes upscale the data from lab to pilot or industrial scale. As you know, when we talk about data at laboratory scale, we're also talking about high uncertainties for the energy, the material flows, or the waste, and there is a need sometimes to extrapolate the data. Okay, let's take a practical example with the lab scale assessments of lignin-based polyol, which is one of the steps in LIGNICOAT projects. So this table is the associated life cycle inventory with some of the inputs grayed out for confidential reason. And this is here the associated climate change impacts, approximately 16 kilograms CO2 equivalent for 1 kilogram of polyols produced, which is quite high. So in these slides, I made the list of the input or output that could be changed at pilot or industrial scale. So first we could change the solvent, which is the tetrahydrofuran. We could change it for its bio-based version. So it has been studied. We found a paper dealing with the bio-based tetrahydrofuran. So we could model it in the software CIMAPRO. Then according to its technical sheet, we also have the same solvent, the tetrahydrofuran, that could be recovered at 90%. So this is something that we also took into account. Then we also have the water for cooling that could be recirculated. We also removed the drying oven and the rotary evaporator, so we also lower the energy. And finally, we made the assumption that half of the electricity at industrial scale could come from renewable energies. So here in this table, this is the new inventory with the updated values in yellow. So we'll skip the detail of every calculation, but if we recalculate the associated impacts, this is what we get. We observe a reduction of almost 80% in comparison to the previous impact for the climate change impact category. So this is just an example on how the conclusions at lab scale can be inaccurate sometimes and not relevant to compare with the products in the market where the sustainability was already optimized. So this is what we try to do for every step, every sub-step in the process in order to get relevant results for the final product, which is the biocoating. And to give you an example of the results that we obtained, this is the final overview for one of the coating under assessments. So in this picture, we highlight the environmental and socioeconomic results of the value chain to produce a biocoating for fire protection. So we're starting with the craft lignin, then we produce the polyols I was talking about in the previous slide that we made from fractionated lignin. We also produce a biopolyurethane with bioisocyanates, and the functional unit is 1 square meter of biocoating, complying with standards for fire protection of wood. So this was compared to traditional petro-based counterparts, and you can see in green the associated single score in climate change value for each step. And we also have the price per kilogram, so this was for the life cycle costing. And finally, on the left, you have some of the conclusions and recommendations for the end user. So this is what I wanted to show you today, given the time I had. So let's talk about it during the open discussion if you have some questions. Thank you.
Thanks a lot, Léo, for this nice and quick overview of the results of your project. I will go to the next presentation from Yolanda Nuñez from CTME and the THERMOFIRE project. Yolanda.
Thank you, Andrea. I share my screen.
And okay, we can see the screen and you can put it in presentation mode.
Right.
In the meantime, I remember all of you the mural session that will start after the presentations. I'll send again in the chat the link.
Okay.
Okay, that's great. Perfect.
Well, my name is Yolanda Nuñez. I'm in charge of the sustainability area at the Miranda de Ebro Technology Center, CTME. I'm also responsible for carrying out the life cycle assessment activities in the THERMOFIRE project. First of all, I would like to thank the organizers for inviting us to this interesting workshop, both on my behalf and on behalf of the THERMOFIRE Consortium. We really appreciate the opportunity to be here. And I'm pleased to introduce the THERMOFIRE project. We focus on developing novel bio-based and recyclable thermoplastic composites. These materials are reinforced with natural fibers and have enhanced mechanical properties and fire resistance, all achieved using bio-based halogen-free flame retardants. One key element in THERMOFIRE project is using bio-based material as feedstock, including 100% bio-based polymers, bio-based flame retardants, and natural fibers. We aim to create 3 prototypes targeting different sectors: housing for electric car batteries in the automotive industry, seat shells for aircraft interiors in aerospace, and non-woven fabrics for the textile sector. An important task within this project is assessing the environmental sustainability of the developed bio-based composites. To achieve this, a comparative life cycle assessment is being conducted, comparing traditional petroleum-based products with THERMOFIRE's bio-based alternatives. This assessment is now taking its first steps. Additionally, economic, social, and circularity indicators will be evaluated to provide a comprehensive view of the project's impact. The project, co-funded by the European Union, will run from June 2023 to May 2027 with a budget of 4.47 million euros. Here you can see the consortium behind the THERMOFIRE project, led by Avanzare. Our consortium consists of a well-balanced group of 12 partners, including 2 research and technology organizations, 4 large companies, and 6 small and medium enterprises. Currently, the life cycle assessment activities of THERMOFIRE project are in the goal and scope definition stage. The main objective of this life cycle assessment study is to compare the environmental behavior of traditional petroleum-based products with the bio-based THERMOFIRE alternatives. This comparison will allow us to understand the potential environmental benefits of the THERMOFIRE solutions and guide decision-making towards more sustainable options. Our life cycle assessment focuses on several key aspects. First, we assess the raw materials, including bio-based polymers such as polyamide 11, natural fibers like cellulose and flax, and bio-based flame retardants. These materials form the basis of the bio-based thermoplastic composite we are developing. The scope of the life cycle assessment also covers the transformation process of this raw material, as well as the manufacturing of the 3 prototypes that we are evaluating. Additionally, we are analyzing 2 end-of-life processes, mechanical and chemical recycling, to assess the full life cycle of the products. Overall, we are assessing 14 product systems, each defined by a specific functional or declared unit. This includes 1 kilogram of each material, 1 test piece of each thermoplastic composite, 1 physical unit of each prototype, and 1 kilogram of recycled material associated with the recycling process. For each of these units, we'll consider other factors such as composition, property, dimension, quality, and lifetime. Moreover, we have identified current fossil-based alternatives to compare the environmental impact with the THERMOFIRE's bio-based solutions. Regarding the life cycle impact assessment methodology and types of impact, will follow the European Commission Product Environmental Footprint Guide. Moreover, the different data quality requirements for each data collected in the inventory phase will be analyzed. This is an essential part, not only to ensure the accuracy of the results in each individual assessment, but also to guarantee the reliability of the comparative study. The next step involves developing detailed flow diagrams for each process under evaluation. Once the diagrams are complete, we'll move on to identify and quantify all mass and energy flows associated with each unit process. In parallel, the same approach will be applied to the fossil-based alternatives. And regarding the challenge we anticipate we will need to address in conducting this study, based on previous experience, we can point out first data availability, especially for emerging bio-based materials and technology. Additionally, geographic variability plays a significant role. Factors like feedstock availability, soil types, climate condition, agricultural practice, and regular supply chains can significantly influence the environmental assessment of bio-based products. We must also account for land use and biodiversity impacts. These indirect impacts are also difficult to evaluate. Similarly, end-of-life scenarios require careful modeling. Another challenge lies in the low technology readiness levels of THERMOFIRE systems. Predicting industrial-scale environmental impact based on lab-scale or pilot-scale data is inherently difficult, given uncertainties in process performance, material yields, and resource efficiency. Moreover, in conducting a comparative life cycle assessment, consistency is key. Defining boundaries of comparable systems and ensuring functional equivalence are essential for fair assessments. And variation in data quality between the two systems must also be addressed to avoid biased results. And this is all from my side. Thank you for your attention.
Thanks, Yolanda, for your presentation. We can now go to the next presentation. Again, Federico Busio, representing another project called ZeroF. So Federico, you can go ahead. In the meantime, I'm going to send again the link to the mural in the chat so you can get access, and we will then use it soon after our presentation. So Federico, the floor is yours.
Thank you. Hello again. This time I will be presenting the project ZeroF, which is a project that aims at replacing PFAS in upholstery, textile, and packaging material again. So the project includes 12 partners from 9 countries. The list of partners is here. There are some universities, of course, research and technology institutes, and commercial industrial partners. The coordinator is VTT from Finland. As I said before, so the objective is double. The first one is for paper takeaway containers, disposable containers, paper-based. The replacement of the PFAS, which is used to confer the hydrophobicity and the oil phobicity to these materials, and also in textile, the use of a ZeroF molecule to replace the PFAS, which are used in upholstery textile, such as sofas or textile for car seats, are all hydrophobic and stain resistant because they contain PFAS. There is the development, of course, of proprietary technology, and for the textile, this technology is called Ormoser. The issue with of course, with the two type of materials is that, for example, for paper-based material, even those ones that are without plastic lining and that therefore are fully compostable, if the oil and water repellent barrier has been obtained through the use of PFAS coating, there is, however, still a contamination at the composting level. So the resulting compost will contain high traces of these molecules, which are bioaccumulating, persistent, and they're called, for this reason, forever chemicals. For the textile, in this case, the example comes from outdoor textile, but could be applicable also to upholstery. The release of PFAS molecules occurs at the moment that you come into contact with the textile. In terms of emission inside, for example, carpets or sofa, after friction, with due to use, these microfibers that are released due to friction contain PFAS that are then breathed in the indoor environment or accumulates in dust. And also PFAS are also released during the washing process and the drying process, and therefore they end up into the wastewater system, and therefore end up in rivers and eventually contaminate, as we might know, contaminate also the freshwater supply. The project consists in the development, therefore, of two types of coating formulation, one for upholstery and one for textile packaging, starting from the coating building blocks, which are developed by two partners, VTT and Fraunhofer. Then the formulation of the coating based on the feedback of the industrial partner, LATAT for textile and Yangi and VTT for the packaging part. And then the concept validation and the scaling up of the project. Therefore, even here, there is again the application of the CSIC Sustainable by Design framework by LIST in collaboration with TEMAS Solutions, where we perform the safety assessment first. For example, when defining the coating building blocks, when designing the coating building blocks, in terms of choice of chemicals that will make these building blocks. There is a safety assessment, there is an environmental screening, and then there is the coating formulation. Again, what type of process is used, what type of chemical are used. From the LCA part, of course, we consider all the material and energy inputs and the impacts that derive from the production of the coating compound. And then the final part will be running the life cycle of the production process of the product, while with the introduction of the bio-based coating against the reference case, which uses PFAS. In this case, we perform also a social life cycle costing, and as a social assessment, there is a technology acceptance evaluation of the project. Where the project is a bit older compared to SuperBark, it's in its last year. However, the challenges are quite similar. Once again, what I said for SuperBark apply to ZeroF in terms of life cycle inventory building. Collecting data is time consuming and tedious for the laboratory, for the chemist. Therefore, there is this challenge in communicating the data, correct data, accurate data on time to provide the support that the Safe and Sustainable by Design framework requires. Additionally, there are data gaps at database level for all the precursors that are used for the synthesis. As I said before, databases are not complete. Sometimes reactants are missing, so I don't have the supply chain impacts for the production of that reactant. And I have to rely sometimes on literature data when possible, when also it's not too outdated, or balancing generic reaction, which sometimes, because these are novel molecules, sometimes it's not easy to define a stoichiometric reaction for these reactions. At least for me, not being a chemical engineer. Difficulty in predicting also this is another aspect that applies to the moment that we come into production of the product and the use of the product. This novel molecule, as well as of course the reference molecule, they undergo transformation and degradation. For example, due to exposure to sunlight, they might degrade into something else. And we, at the moment, for the novel part, for the novel molecule, we do not know in what this molecule may transform themselves, and therefore the evaluation cannot be performed if we don't know what are the degradation products. And once again, the issue of the characterization factors that are at impact assessment level, not knowing what molecules originate from these novel compounds, at the same does not allow to calculate the characterization factors for the impact assessment method, and therefore there is a underestimation of the environmental impact. The reference material in this case is the PFAS used in both paper coating and textile coating. PFAS are heavily protected by trade secret, the PFAS molecules and composition. Their production is not transparent, and data sets that describe how this molecule are made are not product specific, generic. I found, for example, one single data set that describes the production of PFAS, generic PFAS. Therefore, without truly knowing what are the impacts of producing a PFAS, there is, of course, a bias that is introduced towards the bio-based molecule. Given that this project is more mature, we managed to also evaluate the obstacles so far. The interpretation of the results, of course, as I just mentioned, brings a high level of uncertainty, a subjectiveness of the choices that in this case I made to model the molecule. Due to the fact that there are considerable data gaps on the chemicals, characterization factors, and completeness of the data sets. There is therefore a question that arises in the Safe and Sustainable by Design framework, the step 4 for the environmental sustainability assessment. How can it be accurate and of value if we don't have representative data and information? For the step 2 and 3 of the safety assessment, for example, the speed of the innovation process, and therefore the evaluation of the chemicals that are used, especially with the according to the regulation, to the toxicity regulation, it's much slower, takes time. Therefore, the assessment may be often based on incomplete or absent information on the many chemicals that are used. Therefore, okay, you pass the step 1, 2, simply because there is no information in the databases for safety assessment, and also requires competent and experienced professional figures to perform the safety assessment. Overall, the workload of the Safe and Sustainable by Design framework is very high, and is not as reactive as to support the development of novel molecules. Thank you again.
Thank you. Thank you also for the many challenges you have put on the table, but maybe not sure we'll find solutions, but at least we can put them on the table. So then last talk is from Ana Díaz from Geiker. Ana, if you would like to take the floor.
Yes, thank you.
She will discuss about the fraction project. So
how can I?
yeah, we can see the screen.
Yeah.
Just need to put it in presentation mode.
Okay, now, hopefully.
It's okay.
Perfect. Thank you very much. First of all, I would like to thank the organizers of the organization of this workshop for inviting us to participate. My name is Ana Díaz. I work at the Geiker Technological Center. Just a brief introduction, we are a research center located in the Basque Country in the north of Spain. Our main specializations are in biotechnology, also functional and sustainable polymers, sustainable composites, and recycling and circular economy, which is the area where I am working. We have a team specialized in LCA, also social LCA and LCT. So today I would like to very briefly present our experience in the Fraction project. The Fraction project is a European project funded by the BBI. It has been running from June 2021 to May 2024, so it's been recently finished, let's say. And the project consisted in developing a new or novel lignocellulose fractionation process to obtain high purity lignin, hemicellulose, and cellulose streams, and converting them into high added value products. So the base of the let's say this organosol fractionation process is using a mixture of gamma valerolactone, a green solvent, and water for this fractionation of the biomass. So the process, let's say, was already tested before starting the project. So the aim was to upscale it from TRL3 until more or less TRL4-5. So it has several advantages. I will not go over them, just to be brief, but it allows high biomass loading, a flexibility of feedstocks, mild conditions, and has almost zero solvent waste, etc. So the project, the consortium, we had 2 large companies, 5 SMEs, and 5 RTOs, where one of them is Geiker, and it was led by the CSIC, in a Spanish institution. So as I mentioned, the main objective was to demonstrate this novel lignocellulose biorefinery scheme that allowed to obtain high purity and high quality lignin streams, lignin and hemicellulose, while maintaining a high grade cellulose stream as the main output. Okay, so the main objective was this, and obviously we had to demonstrate as well as the sustainability and the techno-economic viability of the whole process. For this, we were in charge of the life cycle assessment jointly with the University of Rey Juan Carlos, and we also performed obviously the techno-economic assessment, which was done by PDC, Process Design Center. Here you can see more a summarize of this figure of our, let's say, scheme for the LCA, where we analyzed on one side the fractionation itself, that is to say the conversion of different biomass feedstocks into the 3 main, let's say, process streams, which are cellulose, hemicellulose, which went into furfural later, and also lignin. And then we also analyzed every and each, let's say, downstream valorization route. So for cellulose, for example, it was into pulp. For hemicellulose, we analyzed the conversion into alkyl lactates on one side, and ketoses and other building blocks for PEF on the other side. From furfural, we had the conversion into malic acid, then succinic acid, and then these building blocks would be used for either polyurethanes or PBS. And then in the case of the lignin stream, we obtained polyols, lignin polyols, or either we use the lignin itself to be introduced into phenolic resins and then phenolic foams. So there were a lot of, let's say, valorization routes available. So the idea was to model and upscale each of these downstream process routes, and then also to benchmark with the market products. So in essence, well, looking at the challenges that we faced in the LCA, I think I'm not going to go very in detail because most of them have been already mentioned. They are not new to any LCA practitioner here. Obviously, we had the issue of inventory data collection because we had multiple processes and sub-processes, and most of them were at lab scale, some at pilot scales. We also had some processes at industrial scale, but we also had their issues with confidentiality issues, let's say, which means that we did not have the inventory data available. This also introduces a fair amount of, let's say, uncertainty. Linked to this are the data gaps. Obviously, the inventories were complex. We had many chemicals. Some of them are not included in the databases, so we have to resort to either stoichiometry modeling, process modeling, simulation, etc. This has already been mentioned before by my colleagues. Another usual issue that we found in biorefineries is the allocation of impacts. In our case, when we analyzed let's say, the environmental impacts of the fractionation itself, we didn't have to use allocation since we used the functional unit of 1 ton of biomass processed. But when we went into the downstream processes and we want to analyze the environmental profile of each intermediate or end product, there we had to use an allocation. And in our case, actually, we used 3 different allocation schemes. We tried the mass allocation, the economic allocation based on market prices, and also energy allocation, since the energy consumption was, let's say, the most relevant factor for our process in terms of environmental impacts. Then also there is the question many times arising in biorefineries of whether or not to include biogenic carbon. In our case, since we were using the environmental footprint methodology, and this methodology does not exclude the biogenic carbon, but it is calculated separately so we can see how much it is affecting our impacts. And finally, the benchmarks, obviously, because, well, since our processes most were, even though they were optimized using simulation, process simulation, many are still at lab scale or pilot scale. So we found that some of the chemicals did not perform better. They perform worse, environmentally speaking, compared to market, let's say, products, fossil-based or conventional products. So this is also another issue. And in particular, some of the categories most affected were climate change or water use or land use for bio-based products. And this would be a very brief summary. I did not want to take a lot of time, so I hope we can have a fruitful discussion now about these themes. Thank you very much.